So welcome everybody. Thank you for signing up, attending, speaking, or moderating at the 6th annual Montreal Oscillometry Summer Seminar. Let's see, here we go. So as I said last year and again this year, well, 2020 and 2021 were indeed different. But the Zoom platform has allowed us to achieve attendance, which probably would not happen in person. We had 204 attendees on average each of the 4 sessions last year from 27 countries. And these folks represented 38 universities and 19 corporations. This year, when we thought about doing it in person, I would have had to run a lottery because our auditorium has a restricted number of 55. And a quick shout out to our industrial partners and government partners who are either helping defray the costs of organizing this or contributing to funds to help me with my research projects. Also, a shout out to the Respiratory Effectiveness Group who kindly hosts the recordings from the previous years, and the recordings from this year will also be posted on this website. You can access it anytime if you want to catch up with anything you missed. However, none of this makes up for the fact that our oscillometry networking suppers can't happen virtually, and I remain ever optimistic that next year we will all be together around a dinner table. Fingers crossed. So with that, I'll welcome you. We've got a great lineup this seminar series starting today with Sylvia's talk, followed by Jason, Sam, and then finally Jeff is going to share with us his thoughts on quality control. But first, I'm going to take you on a quick stroll down the wards of the Lakeshore General Hospital, and then a quick jaunt over to my clinic afterwards for 4 clinical vignettes. So as many of you know, when I talk about oscillometry, I acknowledge that it is sophisticated, it's elegant, it's complex, and extremely interesting. But not all the clinicians are engineers, and I can tell you that they actually get shivers down their spine looking at this sort of analysis. And I try and simplify it to something more friendly, and that is pattern recognition. And happily, a lot of these patterns seem to be holding up in other groups, and it remains to be seen how widely these are adopted, but that's one approach that I take. The other approach was a project that Jeff and I hatched, and kindly Grace Paraga and Rachel Eddy were accommodating and volunteered their data, where we were able to link both the frequency dependence of resistance and the reactance area to the ventilatory heterogeneity as measured by Grace Paraga's technique using hyperpolarized helium. And I'll come back to that later on. But the reality is, as long as oscillometry is relegated to the labs and the research projects, we're never going to go forward in clinical practice. And there's simply no substitute for getting your hands dirty with a technology. And fortunately this year, as we resumed in-person visits here in Montreal, as you did elsewhere around the world, I began measuring oscillometry at each patient visit of each patient beginning in September. And so between September and the end of June of this year, we've measured over 1,000 studies from 737 patients. So we have some repeat studies and some, but importantly, across the spectrum of disease, more than I had looked at previously, limiting myself mostly to COPD in the past. And for example, the plot on the right side of the screen just shows you the distributions with box swarm plots of the reactance area across that same spectrum of pathology that I see in my everyday practice. The other note of oscillometry at the Lakeshore General Hospital is we are now able to get objective lung functioning in patients not previously amenable to spirometry. And here's a young 3-year-old soccer player who's now keeping up with the other kids because we diagnosed and treated his asthma, and another patient who's got cerebral palsy and repeated aspiration supposedly, but it was actually his asthma, which we were able to document and treat. Even though he had a tracheostomy, we can make adjustments for the resistance through the ET tube and understand what happens with therapy. So a quick couple of cases from the wards. They're not to present in detail, but really to illustrate a point. And here's an older ex-smoker who had presented with a massive pulmonary embolism. And you can see the central clot in the pulmonary arteries indicated by the red arrows. And he was appropriately treated, but remained dyspneic 4 days into his therapy on the wards. And so I was consulted to say, does he have COPD? And should we be treating it as well? And had this been several years before, I would have said, well, that's a good question. It's quite possible. why don't we give him some therapy with a long-acting bronchodilator or a dual bronchodilator, and we'll get spirometry rather when he's able to do it. But I was able to do oscillometry on him safely. And this is essentially a normal oscillogram. And I was confident enough with it to say he does not have COPD. I did not give him COPD therapy. He got much better in the coming week. And 6 months down the road, through my office, we had him effect a full pulmonary function test, which, as you can see, is entirely normal. The next vignette is a lady who's followed at another hospital where they have a large pulmonary hypertension clinic. Because she lived locally, she often came to our hospital, and on the chart was this diagnosis of end-stage COPD requiring long-term oxygen therapy. And she also was noted to have chronic thromboembolic disease, having had a filter placed, and was on lifelong anticoagulation and had pulmonary hypertension. She had never been able to perform spirometry, so the COPD remained undocumented from my point of view, and yet with therapy, she remained quite dyspneic. And when I reviewed over her CAT scan, if she was end-stage COPD, I would have expected some structural changes in the lung parenchyma, which I didn't see, so I was a little bit suspicious. So I did oscillometry on her, or she did oscillometry, which she effected with a very good quality control. And I think Carol, who's in the audience, may have in fact done this study. So thank you, Carol. And here we see an oscillogram which shows changes you might see with COPD. There's certainly ventilatory heterogeneity, if you believe the slide I showed you previously. There's a frequency dependence of resistance, and there's a large reactance area, although probably not as large as I would expect for somebody who had end-stage COPD, quote unquote. But really what I think the key here is the 400 micrograms of salbutamol, which resulted in a complete normalization of her oscillogram. So that would be not what I would expect with end-stage COPD, and I suspect that she had asthma or at best, if you will, ACO, an overlap. But certainly this is not going to be the cause of her oxygen dependence. So we were able to send her back to the mothership with a little note saying, we don't believe that she has the COPD is contributing to the hypoxemic respiratory failure. And so to address the pulmonary hypertension, and she's relatively young, whether or not an endarterectomy will be in her future depends. She has a number of other challenges. So what we'll do now that we've left the wards is we'll jump in the car and trot on over to my clinic, which is a 10-minute drive. And this is a follow-up from 2019 when I'd presented this guy who perplexed me because he was really a paradox. And you'll see what I mean in a moment for those of you who weren't at the 2019 conference. It was in person, so only a few of you probably were. So this was an older gentleman who was a remote smoker. He was very symptomatic with a COPD. I had managed to convert him from a frequent exacerbator to an infrequent exacerbator by instituting suppressive zithromycin therapy in 2017. Now, when I had screened my practice back in 2012 for alpha-1, he was the one ZZ genotype that I identified out of everybody. He was well at the time, he had reasonable lung function. He just was not interested in any form of augmentation therapy, despite my discussing it with him. I knew that he didn't have coronary artery disease, and his symptoms fluxed, as you can see, depending on what was going on. Now, over a 5-year period, he had lost 50 cc's a year on the FEV1 and developed interval gas trapping. And his CT scan on the left is a CT scan as we normally look at them. And probably for the clinicians, you'll appreciate the emphysema in there, especially in the lower lung zones. The slide on the right is my own personal favorite. I use Osirix as a software for my CT scans, and I can do place with some filters. This happens to be VR bone and a 3x3 filter placed on it. And for me, it makes the changes pop out to my eye more easily. And again, you see what I described on the first CT image. And if you don't believe that, the chest imaging platform down at the Brigham in Boston has a software is a software that's layered onto the Slicer software. And this is written by Raul Estebar, who may or may not be with us if he's back from holiday in Spain. And thank you, Raul, if you are. I won't spend time on describing the histogram, but we do get these statistics from it. So the black is the whole lung emphysema. The red bar is my local threshold, which is 10%, 6% if you read COPD gene papers. And this is simply looking at the proportion of the lung, the percentage of the lung that's below a certain density threshold, and it's been previously correlated to be the equivalent to pathologic emphysema. And the next two bars are simply right and left lung. And then we have the upper, middle, and lung zones on the left, and the same thing on the right. And what you notice is that there's this upward trend, meaning that there's more emphysema down below than up above, which is the opposite to what we generally see in central lobular emphysema, and might be what you expect in alpha 1. Anyway, this was my 1ZZ alpha 1, and this is what I saw, and this made sense. What didn't make sense, of course, was that his oscillogram remained normal or borderline abnormal over the same time period. You can see here by 2018, the X has just gone up over my local threshold, which is the 10 on the absolute centimeters of water per liter. And likewise, he was sort of bordering into a frequency dependence of resistance. And this 10 actually comes from Brian Lipworth over in Dundee. But when I took Brian's idea to my own practice, it worked very well. So thank you, Brian, if you're out there. So this is the slide that I told you I was linking the ventilatory heterogeneities measured by Grace's technique with the reactance area. So a couple of months after I presented him, there was no resolution as to why he demonstrated this paradox. He visited Grace's group in London, Ontario, and he himself underwent the functional imaging. And these are his images, which you can see definitely there's marked ventilatory heterogeneity there. And by this time, his oscillogram was abnormal, but not as abnormal as I might expect for somebody with this degree of lung disease. I couldn't do too much more with it. He was my only ZZ, so I just looked at the upper to lower lung ratios of low attenuation area, that emphysema metric. And statistically, anybody who had either one or the other of the Z and S genes, the heterozygotes, they seem to be lower than people who were at risk because they had a low level but were MM in my workup, or their levels in fact were normal. And there was a trend, but it wasn't significant, for the AX to be lower in those that carried one of the two genes, S or Z. So this next case, which may or may not have anything to do with the previous case, is a fellow who came to me for a second opinion on farmer's lung. He was a lifelong non-smoker, but he'd been quite symptomatic for a decade and a half. He'd had a couple of pneumonias, only one documented with a chest x-ray, so I wasn't so sure about the farmer's lung. And his father died at a young age of an unspecified respiratory disease. Now here is his full pulmonary function, showing that he's got airflow limitation on spirometry, gas trapping on lung volumes, and his diffusing capacity is low. And note, he was a non-smoker. And here is a CT, and he's got obvious lower lung zone emphysema, which we can see quite nicely with Raoul's software. And again, this lower zone predominance of it, and well above the threshold that you would see as normal, in fact, similar to the other case. And here is his oscillogram, another paradox. Well, I'm no fool. When I see a pattern, I recognize it. And this is the first case I presented. And here's the fellow who came to me for farmer's lung. And so I normally don't work up my asthmatics for alpha 1, but maybe I should, because he too is a ZZ. The literature wasn't terribly helpful. I'll just leave that up. There was only one paper that included any amount of ZZs, and their reactance areas were statistically lower than the others in a ZZ, but they were all within the normal range. And so we'll leave you with this last slide, anecdotes from the wards and the clinics, that we have a broader application of oscillometry, and I gave you a couple of clinical vignettes demonstrating that. And to be fair, I wanted to look at the limitations of oscillometry, in that we got normal oscillometry results in the face of undisputable disease, which is going to be some of the hard questions that clinicians are going to ask us as they start using this technology, because if I'm seeing it, they're going to see it. Or do we make lemonade out of lemons by saying these situations are an opportunity to understand and tweak our models better to better reflect reality? So I throw out for discussion, and I'll hand the podium over to Peter. Is a mechanically homogeneous emphysema phenotype possible? So thank you for listening, and I'll stop sharing my screen and hand the podium over to Peter.
Thank you very much indeed. Ron, that got us off to a cracking start, and you have demonstrated, despite my concerns, that you can get through considerable achievement. But also, as well as doing the welcome, and which is very graciously given, as well as that, you've also given us plenty to think about, and it's a good way to set up a meeting like this, where quite often we get bogged down in the theoretical, and we make the data fit our models rather than our models fit the data. And I think your last cases illustrate why we need to think carefully about the assertions we make. Let me pick up just a couple of things. Firstly, I think the first two cases illustrate the value which we often talk about but don't often present, of being able to make an objective measurement when you think a diagnosis is due to something else. And it's very elegant to know that the first guy did not have COPD, clearly didn't, and clearly then recovered. And that the second person's problem was really down to their pulmonary hypertension. And that is a real issue in that case, because that was overtreatment, and unnecessary overtreatment of a problem that wasn't really there. In fact, the problem was the asthma in the second case. So that would not have been possible without without the use of oscillometry, which is simple and quick and readily available. So I think we can all say, yep, these are really good examples. The challenging part is in the last two cases, your ZZ examples. And I'm not sure I've got a clear explanation as to what is going on. The records look pretty normal, but I am very intrigued, firstly, by the fact that the the first case you presented went on to develop really quite abnormal oscillometry subsequently by the time they got over to London, Ontario. It could be a climate shift, it could be a cultural change, but I think it's probably physical. And therefore, everything's down to the timing of these measurements in the time course. But the second person hasn't done that. I mean, if you look at the lung function in those individuals, what I was struck by was the extent, particularly in, I think, the second case, at least early on, and the extent to which the vital capacity was spared in terms of loss of lung function. I just wondered whether some of the reason for the apparent, well, for the normal values in oscillometry was the fact that these people were compensating for the mechanical problems during tidal breathing by increasing their operating lung volumes. And I think then you reach a stage, perhaps with your example of a person whose lung function clearly was worse on oscillometry over time, where that was no longer possible. And that just raises two questions in my mind. I don't have any answers. I'm going to throw this open to discussion now. But the first question is, to what extent during tidal breathing measurements like this, in conditions where you have an entirely parenchymal disease, and I think that would be the inference of the CT data you showed, would you expect to see abnormalities in the airway and therefore actually in the AX? And also, what is the timing of the natural history of changes in oscillometry compared with changes that we're more familiar with forced tests of forced expiration, which we kind of feel, at least in large normal populations and in COPD, that we have some idea. So I've not got an answer for you. I've got some suggestions, but I'd be very interested to hear from the rest of the community as to what their thoughts are. And here's Jeff.
Yeah, I might put out a first thought. The CT, was it CT? But certainly it was MRI. Those are done supine. And so they're at a lower lung volume than the oscillometry, which is usually done upright. So if you're going to trap gas and see it in the MRI, that's the way to do it, is to go supine. And you might see it relieved when you come upright, and the oscillometry would be normal. It's one possibility.
That's true, I think, Jeff, and I think that's a very good point, because posture, along with, well, posture is another variant on volume in this, but posture is an important consideration. But there's little doubt that the spirometry data and the detailed lung function data does show clear abnormalities, including, actually, interestingly, I think in the, can't remember if it was the first or the second case, a somewhat a decrease in airways resistance total, which wasn't really reflected during the oscillometry. And that puzzles me a little bit, because I would have thought that the oscillometry might have picked that up, which it didn't seem to have done. And I don't know if you've looked at your clinical data, Ron, about where you've got data on airways resistance and contemporaneous oscillometry as to what the data, how well they agree.
Yeah, you get R's that are pretty good in the 0.6 range, which is not bad at all. To speak to Jeff's comment, which I think is important, I've got data that I've never published because it's simply too small, but there's definitely a measurable effect on oscillometry in my practice, whether you're supine or sitting. And in 10 cases, actually, I related the degree of change to how much emphysema the individual had. In other words, it's seemingly that if you've got lots of tethering pulling on your airways, the effect is greater than if you don't. But in 10 cases, it's really hard to say anything, and I haven't had a chance to go further. I think we'll have the last word from Zoli, because I suspect he may wonder if intra-breath mechanics might be a way forward to understand these cases. So Zoli, why don't you give us your thoughts? Your mute is on, so unmute, and we should be good.
Sorry, your prediction was wrong. Sorry, I'm not addressing intra-breath now. Just a very little item in the methodology. In addition to the posture difference which you raised, Jeff, probably the lung volume in which the CT or MRI was taken is also a big difference. In higher lung volumes, the structure might be more homogeneous or the contrary.
Yeah.
Thank you.
I do know that Grace's MRI is done at tidal volume, half tidal volume above FRC. So.
Okay. I thought it was FRC plus 1 liter. So, okay. We're not going to resolve my paradox, but I would appreciate if people could think, and when you see me next, share your thoughts with me. I don't want to intrude on Sylvia's time because we're 2 minutes over this talk. So Sylvia Verbank from the Free University of Brussels needs no introduction, and we're honored to have her speak to the oscillometry community, linking a technology she's labored with long to oscillometry. So Sylvia, the podium's yours, and thank you very much for speaking to us.
Thank you very much, Ron. I'll try to share my screen, and I know Jason is there to help me if I can't work it out. So that's great. Let's see if I can share this. Do you see the presentation right there?
Perfect.
Okay, so let's go. In fact, yeah, it's a little bit bizarre that I should be kicking off this meeting with my presentation, because I'm really an outsider to this crowd. My trade is gas mixing, and here I'm essentially in a lung mechanics crowd. But the reason I came with this first slide 3 years ago, that was live in Montreal, is because I'm really convinced that there's a common ground between gas distribution and oscillometry, as it's called now, and that it's situated really in the sense of looking at the way the convective flow distributions, the patterns of flow distributions are distributed over the tracheobronchial tree. So I'm talking about convective flow over the non-alveolated airways. And so, oops, oh, I did something wrong there. Let's see if I can get the next slide here. How do I get this? And there's, whoops. There's today a slide, voila. And so in the meantime, I have a clue myself that maybe we could test on the other side. And the reason being that I teamed up with Brody Foy, and Brody Foy had these CT-based realistic models obtained in asthma patients. And then he built these complex models all the way to the boundaries of these patients. And he succeeded in doing gas distribution simulations and indices, simulating indices that he could really verify experimentally in those patients. And so I thought, well, without really touching anything in this model, what does the pattern of convective flow look like in this model that he has, and that seemed to work so nicely? And so, yeah, okay, usually we're always put in the same bag, the impedance or the oscillometry measurements in a multiple breadth washout. And our common problem or advantage, depending which
Sylvia,
you choose.
Sylvia, let me
Yes.
interrupt. Your slides aren't advancing. What slide are you on?
I'm on the third slide.
Okay, I think what happened is I gave you false information. What we're seeing is actually your slide deck and not the slide presentation mode.
So shall I
So
stop sharing and maybe try to go?
Yeah, try sharing again.
Okay. Let's see. Oops, where do I go here? Share. It worked a minute ago, but now it doesn't really. Let's see. No, but it doesn't offer me the other screen. You know what? I'm gonna disconnect.
You could just click on the slides to change them if you want, because I think we're all close to our screen, so we can probably follow along like this.
But do you see it now? Because I've just disconnected the second screen. Maybe it's better now.
I see it. We see a slide that's titled "Small Airways Tests" in quotation
That's the one.
marks.
That's the one. Let's take it from there.
You're not in presentation mode. If you want to try hitting that small icon at the bottom right, it might work. If it doesn't, that's okay.
I should be now.
Yeah. So bring your mouse all the way down to the bottom of your screen over on the right.
Yeah.
So we don't see your mouse, and there's that little screen icon just before the slider for size.
Oh, I don't have it. Oh, there it is. Wait a minute. So which one do I take?
The one that looks like a screen. It's right beside the minus symbol on your slider for size on the bottom right of your screen.
No, I don't have that. Let's see. Halala. Sorry about that.
Well, continue with this. We're good.
You can also go to slideshow at the very top, right to just to the right of animations. And if you hit slideshow, that'll start a slide.
Let's just try again. I just want to try again.
That's the one.
Is that okay?
No,
are
we're
we now
still seeing the same thing. It's okay.
Okay, let's just go. I'll just go through the slides this way. Is this all right for you?
This is fine. This worked for Zoltan last year. This is how he did his. So
okay, it must be a European thing then. Sorry about that. So in any case, because we lost some time now, oscillometry and multi-breath washout, they have plenty of in common. Whereas getting measurements at the mouth, and we know that this can be a resultant of plenty of scenarios happening inside of the lungs. Now I need to talk a little bit more about multi-breath washout just to set the scene. And so in its most simplest form, we're looking at a lung being washed out of its original nitrogen concentration just by having a person breathe in pure oxygen. And so some areas or lung portions will be better at it than others, so that we'll have a faster rate of N2 concentration decline than others. This can be between the top and the bottom of the lungs. This can be between diseased and non-diseased portions of the lungs, or essentially they can be portions of the lungs that are scattered and small scattered all over the lungs, but they have to be greater than 0.1 of a cubic centimeter for us to be sure that we are just dealing with convection, and that whatever comes into one of these smaller units is then equilibrated by diffusion instantaneously. And so what I did 3 years ago already, I made this link between FOT, as it was still called at that stage, and the multi-breath washout, because people, especially essentially the group around Ken Lutgen, had already done some work on that. But here I really want to cut right to the chase and concentrate on each one of these multi-breath washout expirations and look inside one such an expiration, whichever one we choose. And then the only way you can see something at the mouth of which you know that inside, we know it from Grace Paraga's ventilation modality imaging, we know there's different concentrations inside, but the only way we can get a reflection of that at the mouth is if there is some kind of expiratory flow sequencing. And this is really what I want to get to today. And so I made some toy models. I hope this is the right word. That's what Brody uses, so I dare to use it myself, to see which kind of expiratory flow sequencing patterns could lead to a positive phase 3 slope. Because remember that in normal people, phase 3 slope somehow is always positive. and then becomes more positive or steeper in disease most of the time. And so the typical sequencing patterns that would give rise to that are seen right there. On the left, you can see basically a phase shift of two signals. So that's flows from both daughter branches at the branch point meeting each other, and then voila, having a phase shift between them. Or it can be a little bit more exotic also, that it's basically what we're after is the expiration, is that within the expiration, there's some kind of flow sequencing between this flow, to the extent that the best ventilated unit is the one to empty first. And of course, you can see that there's differences in shapes of these expiratory curves, but we're never going to see that experimentally with all the noise that comes on top of that. Here I represented the same thing in terms of Lissajous figures, because I gathered engineers from the lung mechanics area would be more accustomed to seeing that. And the dashed curves, they just indicate that in a way, I don't really care what happens during inhalation. We need different average flows into units of the same volume, but otherwise the sequencing that I'm really after is happening during expiration. And so already 3 years ago, I scanned the literature for all these lung mechanics studies, where I thought, well, maybe some distortion in the parenchyma with the airways inside them. Maybe they produce some kind of local flow asynchrony at branch points. And I'm just highlighting this one because I gave a few last time I came, but I'm just highlighting this one from Ted Wilson, and especially because he intentionally really wanted to make the link between lung mechanics and gas distribution. And so the object of this study in particular was to see whether these, what he called the Marangoni surface flow, so the surface tensions of acini that are close to each other, whether these could produce some kind of flow asynchrony, which was the case, to then produce a phase 3 slope. And so his conclusion was that yes, this was possible, but it was a conceptual model, and so it was possible to obtain positive slopes, but also negative slopes. And so then fast forward to this collaboration with Brody, I thought, well, let's have a look at all, without touching the model again. He just has all the gas distribution and the flow set up just by introducing pressure drops according to resistance, to compliance, and etc. And let's just see at what of all these individual branch points, where do we see the positive phase 3 slope? And then it turns out, and that was in a publication before this one, that apparently from the model, I have to contend it, that with the slopes that were being simulated by Brody and produced slopes that were correlated to the experimental values, well, with these simulations, it appeared that most of the positive slopes were generated in generations 5 to 7. And so that was very interesting to us, but then we wanted to take it a little bit further, because then we thought, what exactly is it that produces this flow sequence in such a way? So here you can see the flow, you can see the same thing in a different way. So in generation 4 and 8, you see less of the, these are all the Lissajous figures of all the branch points in that generation. And you see clearly that in generations 5, 6, 7, there's more sequencing, more asynchrony in this case than in the other generations. And then we took it one step further and then wondered, but what is it in terms of structural features that produces this flow sequencing and flow sequencing of the right size? So that's what you see here in these gray areas. So it has to be of a certain sign in order to produce a positive slope. And then with, of course, some of these things are interconnected, but basically the overwhelming message was that it was the heterogeneity in the way the compliance units were disposed in the whole complex thing that produced these flow asynchronies in the way that produced a phase 3 slope that was positive at the mouth. And the resistance was much less of an issue there. We also tried to put the radiuses of 2 daughter branches to the same value, just to see whether that would change anything. But it was really basically the way that some parts are shorter than others, that there's an asymmetry in how the pattern, the compliant units are distributed over the lungs. And so that's, from a diagnostic point of view, it's like super interesting, and also explains why, for instance, if you have a normal subject and you just bronchoprovoke a normal subject, these phase 3 slopes, they go up by 2-3 fold, so they go up enormously. And of course, if some of this mechanism could be due to this, then you can imagine that if there's one larger airway that gets shut off, that this effectively then affects the architecture and the distribution of where these compliant units are. And so, okay, to me, that was really very exciting, although I realize that even in this stage, we haven't really gotten to the bottom of it, in the sense that, why does this really happen in generations 4, 5, 6? Why doesn't it happen further down? And then to answer some of these questions, then Brody also made a toy model, but I think that some more extensive and realistic reorganization of the bronchial tree would be needed to really get to that. And okay, this is what is of our interest, being gas mixing people, but I can't imagine that it doesn't have at least an influence also on the oscillometry indices, and maybe better still, that there's some way to obtain oscillometry indices that make this effect become of asynchrony become more apparent, and in that sense also become maybe more diagnostic for certain situations, of course. But as I realized with the gas mixing studies, there's only so much that you can intuitively grasp with a model with just a few units in parallel and in series. And so for gas mixing studies, it was clear that we needed a model like the one of Brody to really sort things out. And I have a feeling that for oscillometry, the same could be true. And from what I understand, if you want the time dependence to really play an important role in all this, then you need to solve everything in the time domain. And apparently that's more a trickier question that has been done by others, but maybe not to look for this particular aspect of things. And that's it, actually.
Well, thank you. And I will turn the podium over to Jason, who will moderate the discussion for Sylvia's talk.
Right. Well, thank you very much for that thoughtful presentation, Sylvia. And I must say, I've wondered on and off over the years exactly the same question as to why is phase 3 always positive? Because the sort of simple-minded view of it is that those regions of the lung with the lowest nitrogen concentration must be emptying first. And as the breath goes on, they switch over, they give way to the emptying, a proportionally greater emptying from the regions of the lung that have a higher nitrogen concentration. And it's very compelling to think that there should be some mechanical explanation for this. And I really like what you've done here, going into all this detail. And I'm just trying to think if there's any way of testing this idea. And it occurs to me that if you think of the lung as a series of balloons on pipes in series and parallel or whatever, let's say in parallel, then you could imagine that the regions with the shortest time constant are the ones that are best ventilated. So they empty first, but they have the lowest nitrogen concentration. But during a nitrogen washout maneuver, the respiratory muscles are controlling to probably a large extent, the rate at which expiration is happening. So it's not like you have a bunch of balloons which are just passively exhaling, but you're controlling that rate with the respiratory muscles, which might suggest that there could be a rate dependence on the slope of phase 3 somehow. And I wonder if anybody's looked at that in detail. I mean, the washout is usually done in a standard kind of breathing rate and breathing pattern and tidal volume. But if you do fast versus slow exhalations, do you get a difference in phase 3? Because it seems to me it would be testing that idea. So I'll just leave that. I'll just put that out there.
Yeah, that's an excellent suggestion. And the only thing that is problematic there is that there's other things changing as well, is that you have this diffusion convection and diffusion front being displaced just because of this flow. But it might be possible if we use the multi-breath washout to tease out and just to get rid of this diffusion thing, that maybe with what is left there, we could find something out. It's not impossible. It's certainly not impossible.
But it is difficult. It's a complicated issue. Ever since Piver and Engel came out with their explanation, what, 40 years ago or something, for diffusive convective interaction, I realized the thing was a mess, and I'd probably never understand it properly.
Yeah, and Antonison, I think, did also some bolus experiments to try and see where this these phase 3 slopes come from. Of course, we know in the meantime there's the gravity that also has a contribution, but it's minor because they did that in microgravity, the group around Kim Prisk. And so we know now for sure that there has to be something intrinsic to the lung structure. And so, yeah, we could maybe try with flow dependence to tease it out. But what I'm really, and that's why I want to do this talk here, is what I'm hoping is that maybe via modeling, the oscillometry people would also be able to find an index that is more sensitive to just this kind of sequencing than another one, and that then, together with multi-breath washout testing in the same subject, we could maybe tease out some patterns. That's my hope.
So Jason, I think Cindy, who's joining us from
I'll
Australia, has a question.
Thanks very much, Ron. Thanks, Jason. And thanks so much, Sylvia. I was really looking forward to your talk. I think the first point I wanted to make was I was so glad that someone finally made the link between oscillometry and washout in terms of time constants, which I thought was always that link that provided that link between mechanics and flow. And so it's really lovely to see you and Brody work on this. And I think the second point I was going to make, and I'm going to try and organize my thoughts a little bit, but it's very intriguing to see effectively the phase 3 slope as a measure of heterogeneity. And what I'd love to see, I guess, is as further work is how you would link this to the oscillometry measure of heterogeneity, which to me would be the frequency dependence of resistance, and how you would reconcile this with work by Lucian and Gillis, where they show that RNE, or resistance and reactance, are fairly insensitive until you get to the point where you've got heterogeneity to the point of airway closure, where you've got closed airways. How would you try? I'd love to see how you would try and model the effect of that on washout, but also the relationship with frequency of dependence. So just some food for thought, but yeah, thank you for this.
Yeah, no, I think actually that it's worth mentioning now. I don't know how many years ago this must have been, that at some point I got a letter handwritten by Cosillo, and he said, yeah, well, I didn't know him at all, and so I read all this letter, and he also joins a paper that he did about airway closure. And so he said, yeah, after everything is said and done, I'm so sure that closure is really an important thing in all this gas mixing business. Maybe you should look into that a little bit more. And well, of course, immediately then I thought, yeah, I'll do that at some point. But I did then a little bit later also on the gas mixing front, when all these data came out from James Hogg, where he just says, look, in COPD, there's like 10% of the transitional bronchioles that are left. So what's happened here when just this whole portion of the lung is closed off? And so indeed I've started to think more in terms of closure. The only thing that still bugs me, and that's probably the same for oscillometry, is that what if closure is also a dynamic thing, that it sort of closes slightly and then it opens up again intermittently during inhalation, and then it just seems to become so difficult. But there again, I have the impression that if the key is somewhere in the structure, we have to, even in the worst case scenario, just with doing plenty of simulations and then doing data mining on them, we have to find something.
Yeah, two points in response to that, if you don't mind. I remember at this forum last year, we talked about perhaps closure being a stochastic process rather than a certain, rather than it being fixed, and it's constantly shifting, as you say. And I can't remember whose talk it was, and I apologize for that. I think the second point I was going to say was that of all this exciting work, perhaps the one disappointing, if I may use that word, from the work is the fact that what you seem to show, you and Brody seem to show, is that it's heterogeneity happening at airways that are a lot more proximal than we've become interested in. All this talk about small airways, and also the series that went in the JP recently, where we were all talking about, well, is small airways really all that needs to be, was interesting, because that's what we think small airway closure. That's where the site of airway closure would realistically happen. But what you're showing is, well, actually, it doesn't need to be the small airways. Maybe it just it doesn't need to be that distal. And so trying to find out, I think, would be interesting.
Yeah, now you said it exactly the way it doesn't need to be. It doesn't mean, because of course, Brody, he makes these complex models, and then as soon as you don't have a CT image of it anymore, he continues to grow airways. And so maybe we need to also change the algorithm of growing, but there's only so many things that you can get to the boundary at that stage. So if the asymmetry of the compliant units would be so much distorted by that to also produce something in addition to the contribution that we already find in generations 5 to 6, which suffices to explain what we find at the mouth. So yeah, there's all these considerations.
Okay, well, this has been a great conversation. I'm going to invoke closure here at this point, because we're impinging on Jason's time. Although, Sylvia, I'm very happy to hear that Manuel Casillo was involved. Manuel was actually one of my clinical mentors back in the day. So it's good to hear that he's still having influence on us these years later. Jason, over to you. Jason Bates is going to be talking to us about fitting branching airway tree models to impedance of the respiratory system. And Jeff Fredberg is going to be moderating the talk. So I'll turn the podium over to both of you gentlemen. Thank you.
Thanks, Ron. Sylvia, can you unshare your screen? Thanks. Can everybody see that? See?
Yep, great.
See that? Good, great, okay. So this is my talk, and I have a couple of disclosures, nothing important. So first of all, just by way of introduction, since this is a talk, this is a symposium mostly about oscillometry, and nobody's actually defined what it is yet. Obviously, as I think everybody knows, you generate an oscillatory pressure at the mouth, flow at the mouth, you measure the pressure, you record those signals, some things happen in the computer, and you end up with impedance. And what we get out of this is the real and imaginary parts, so-called resistance and reactance. And now the question that I'm going to address is, what do you do with that? Well, as I believe I mentioned in a previous talk in this symposium, the most direct path to usefulness is to take those resistance and reactance measurements and calculate empirical parameters. And the one I like the best is AX, because it's an integrated measure that uses more than a single data point. But whatever it is you use, you want to employ those parameters to diagnose disease and prognosticate as to how it's going to go. For example, there's AX. That's the shape, very crude way of what the real and imaginary parts look like over 5 to 30 hertz. So at this level, you don't care what these things mean in the sense of linking structure to function. And this, in fact, is similar to a lot of evidence-based medicine. From the point of view of the patient or the physician, you don't have to care what it means, because if those things are useful for diagnosis and prognostication, then you're good. Now, this august body of scientists, clinicians that are listening today, of course, is not typically happy with that. They say, well, what does it actually mean? So you take your measured resistance and reactance signals, and you want to get some kind of link to structure and function from that. And to do this, you have to use a mathematical model. And the model has to have some structure that bears a useful relationship to reality. And from that, you end up with model-based parameters. And you use these to do whatever it is you want to do. Now, the potential advantages of this, if you can get the right model, is that it makes the search for useful parameters more efficient, because rather than trying this and trying that and seeing if they correlate with your disease, you can go straight to a sort of mechanistically based or structure function link based parameter and probably get there more quickly. And it also provides scientific insight, which is perhaps the major reason why people like those on the call today are interested in doing this kind of thing. So how do you do it? Well, the simplest model is a single unit with an elastance governed by a spring near E and served by a single airway that has a resistance R and an inertance I. And that inertance comes from the mass of the gas in the central airways, predominantly bouncing off the elasticity of that spring. And this model has an equation. There it is. It has a differential equation. And you can calculate the Fourier transform of that differential equation. And from that, its impedance. And that thing there on the second equation there on the right is the impedance of that model. It says the real part is constant and the imaginary part, oh, it should be a plus there, sorry, not a minus, plus I times that stuff in brackets. That's your imaginary part. And that gives you the hyperbolic function at low frequencies and the linear shape at high frequencies from which you can extract E and I. So from this, you could fit that model to measurements of resistance and reactance and extract values of resistance, R, I, and E, and use these as mechanistically based parameters on which you're going to assess your patient. Some time ago, the group I work with used a slightly more complicated version of that model. Here it is in electrical analog form. This basically is two balloons on two pipes arranged structurally in series. And we fit that model to oscillometry measurements. This was impulse oscillometry actually made in obese patients pre and post bariatric surgery. I was fortunate enough to work with my colleagues, particularly Ann Dixon, who was leading this effort, who did some really amazing studies with the bariatric surgeons. And from that, we extracted values of RC, the central resistance, the peripheral resistance, and so forth, and used that to try and infer what may be going on in these patients. And, you know, if a 2-compartment model isn't enough, maybe you can squeeze a 3-compartment out, probably not. Anyway, the question that I want to address today that I've been thinking about lately is, can we fit an inverse model? Because those are inverse models. They're models where we have a decided structure and the model is characterized by free parameters whose values we don't yet know, but we adjust those parameters to make that model behave as closely as possible to the data that we've measured. That's the fitting process. So it's called an inverse model. And from that, we're trying to figure out what's going on inside the lung. Now, those models that I just showed you, the single compartment and the 2-compartment model, they have some tenuous link between structure and function, but they're very crude. And they don't really embody anything that's obviously anatomy. So I wanted to see if we could come up with an inverse model of impedance that can still be fit to data, but that represents lung anatomy more accurately. And let me just say at this point, in order to do this, to have any chance of success, whatever model you come up with has to have a very small number of free parameters, because there can't be too many things that you're adjusting in parallel to get your fit to the data. If you want to get a unique fit and not have just a gazillion different possible fits, all that look the same and you don't know which one to pick. Actually, the first person who, Jeff, I have to thank him for reminding me of this. I did know of this paper some time ago, or this chapter. Jeff wrote a chapter quite some time ago, back in 1989, where he talked about this problem and sort of laid out the general considerations and what the key problems are associated with it. But nobody's actually done it, as far as I can tell. So I decided to have a go at it recently. And the model that I am going to fit these data was one that I came up with only a few years ago that I published. Here's the reference. And this model represents the airway tree as an asymmetric branching structure according to the Horsfield scheme, where the airways are numbered according to airway order. So the highest order is the trachea, the lowest order of the terminal bronchi. Each terminal bronchus ends in a viscoelastic unit. And at any point in this tree, the difference in order number between the two daughters at any branch point is a fixed number. So actually, in this case, it's 2. So we've got an order of n-1 here. One of those daughters has to be n-2. The other one necessarily has to be n-4. And so it goes on all the way down. The advantage of this structure is that by choosing the number of orders n and the Horsfield delta, the difference in daughter order number, you can specify with only 2 parameters an entire asymmetrically branching tree. So those are two fixed parameters which define the airway tree. And for a human, it's a pretty good bet to say that n is 25 and delta is 3. Now, also to model this lung, I had to have a couple of physical properties of the air, and that's a no-brainer. You just take the values of what they are. But here's the critical thing that makes this model potentially fittable, is that I assumed that the ratio of airway length to airway radius was the same for every branch at a value of 6, and there's evidence in the literature that it's about that. I assumed a hysterosivity of the terminal units of 0.15. I assumed that the trachea was 4 times longer than would otherwise be the case if it followed one of the next parameters that I'm about to say, because I chose 4 free parameters, and these are the parameters that define the rest of the model. And this is perhaps the key one. If you take any one of those branches and say, what's its radius relative to the radius of an order just above it, I said that has a fixed value. So in other words, as you go down in order, the airways get progressively smaller by exactly the same fraction. So there's a fixed order-to-order fraction of radius. There's a fixed radius to length ratio apart from the trachea. And so with a single parameter, an additional parameter, you can scale the entire thing. You have to start the radius at the beginning here. So you need, as an additional parameter, the tracheal radius. I assumed there was a respiratory system elastance using this is the constant phase model I'm putting at the end of these terminal units, and they're all the same. And finally, because I'm pretty certain this is essential to describe real data, I assumed there was a compartment right at the front here, which represents the cheeks and pharynx and so forth, which has some kind of proximal shunt elastance, so that when you're oscillating flows into the mouth, not all of it goes down into the lungs. You could also make a strong argument that those airways should be elastic, and there should be an elastic wall stiffness. And in fact, I can put that in the model from the point of view of, but I don't know what its value is, so I can't assign it a priori. But from the point of view of model fitting, the problem becomes too ill-conditioned if you have both airway wall elastance and shunt elastance. So I just bundled them into one effective shunt elastance. So these are the parameters, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters completely define this model. And I've decided that 4 of them, these 4 down here, are going to be the free parameters. They're the ones that I'm going to adjust in the fitting process. And these are the ones that I feel confident enough to assign nominal values to. And that's an important decision, because the more free parameters you have, the less chance you have of success. So I tried to keep them down to just the number that are absolutely, there's no way you could know what they were. So I fit this model to some data that I got from my colleagues at UVM, Ann Dixon and Dave Kaminsky and their coordinators who collected these data. And this is oscillometry data using the tremor flow in a group of lean controls, a group of obese controls, and a group of obese allergic asthmatics, just shown in the color scheme there. And the measurements of resistance on the top and reactance on the bottom are shown by the symbols. The solid lines show the best fit that I could get from that model. And as you can see, just visually, the fits are pretty good. So just by adjusting those 4 parameters, I can describe those curves pretty well. Now, what do those parameters come out as? Well, here's the tracheal radius. So this was estimated from the data, not pre-assigned. And the tracheal radius in the lean control, the obese control, and the obese asthma are fairly similar. They're all entirely reasonable physiologically. And you see the obese controls have a lower radius than the lean, obese asthma lower again. And I haven't yet done a sensitivity analysis on this, which is something I have to do. So I can't give you error bars or anything, but it's moving in the right direction. Here's the airway scaling factor. So in other words, this is the ratio by which the radius of one order is less than the radius of the lower order. And it's all about just over 0.8. It doesn't change with any of those conditions. And it's right in the region that has been described anatomically by anatomists. Here is the elastance. I've called it ERS here, but in the parlance of the constant phase model, it's H. And this is where the big difference is. The lean controls, the obese controls, and the obese asthmatics are getting progressively much stiffer. And that is presumably because first of all, in the case of the obese asthmatics, we've got pretty strong evidence that they do have lung collapse. And this seems to be picking that up. And in the obese asthmatics, they probably got additional airway closure on top of that because of the asthma. And that's being picked up by this model. And here is the central airway shunt, which doesn't seem to show any particular systematic variation that I can determine. Trying to interpret this with these various conditions, trying to interpret shunts a little bit tricky because it's the stiffness of the sort of proximal region where you put your hands over your cheeks and try and make that proximal compartment as stiff as you can. But if you have for example, a constricted lung, then you're going to get more central airway shunting, even though you're supporting the cheeks. And when you get more central airway shunting, because of nonlinearities, it may look stiffer or less stiff. I don't know. I haven't figured that out yet. But basically, there's not too much of a difference amongst those controls. The big difference is that we have major increases as we go from lean control, obese control to obese asthma in the lung stiffness. A progression in airway radius, which scales the entire airway tree. And this scaling factor here basically says that the structure of the lungs in all those groups aren't really any different. So, at this point, it seems to make a lot of sense. So the conclusions are, you can fit an anatomically based inverse model, provided enough assumptions are made, and you can fix enough of those parameters so that you limit the number of free parameters to being as few as possible, and in this case, 4. It turns out that the model parameters that you get when you do this seem to correspond reasonably well, very well actually, to actual airway anatomy. And it predicts that the airway tree dimensions remain relatively unchanged, although there were slight decreases in radius, very big changes in elastance. And finally, Jeff, looking at a preview of this, came up with a bunch of insightful questions and comments. And so I will stop there and hand it over to him.
Thanks, Jason. That's really interesting. And it's nice to see someone kind of moving in this direction, which we started over 30 years ago. But as you said, no one really picked up on it. So, and now you touched on some of these questions. I think each of these questions actually is answerable if someone wants to do it. So first of all, is goodness of fit sufficient criteria for parameter estimation? Right, so you pointed out you can get goodness of fit if you have enough parameters. So goodness of fit by itself is necessary, but really not sufficient. I think we know that. And you also alluded to this question about sensitivity. We really need to know the sensitivity of the model prediction to each of the parameters. If it's not very sensitive, then you're not going to be able to estimate the parameters. But here's the kind of to me the key thing. You can get a set of parameters from your model, but the question is that set of parameters unique? That is,
yeah,
it might be very different, yet it fits the data equally well. It turns out there are ways to answer that question, and I think that should be done in any kind of inverse modeling. These methods were worked out many years ago, and you need to know how well resolved are each of these parameters. So you can get an estimate, let's say, of a central airway size, but maybe you haven't resolved them very well. Maybe a number twice as big or half as big would fit just as well. And then you kind of alluded to this, and this I kind of take exception to this a little bit, because you can get situations where there are more unknowns than parameters or equations, observations, or fewer, like multiple interclass washout. Right? There's only 6 data points, but you get a whole distribution of VQs. Again, there are ways of handling that in a formal way, And even if you've got many more parameters than data, you can figure out which ones are the most meaningful. And then finally, and this has been a long-standing question, what do you do if your data set is incomplete, or there is data that's inconsistent or even erroneous? How do one take that into account in these inverse modeling? So inverse modeling is a well-developed field, and it's nice to see someone finally kind of pushing in that direction. So I'll stop there and open this to, because we're a little over time, open this to questions from the audience.
Yeah, I won't talk again. So Zolly, go ahead. Sorry, you're muted there.
I terribly enjoyed this talk and the comments and the bonus question. And I would probably add a malignant or malus question to Jeff's. But first of all, it was not clear why you complicated your model with different viscoelastic units. If you put a peripheral tissue model which features H and eta, then you should do exactly the same with the upper airway shunt, because it's a viscoelastic unit with a probably higher eta value, a more viscosity, probably, than the lung periphery or the lung tissue. So probably adding a viscous component to the central airway shunt would eliminate the differences between your modeling predictions between the three groups of patients.
That's interesting. Yeah, I hadn't thought of that. And in fact, it doesn't take any more parameters, so I could do that. Yeah, sure.
The other one is very, very malignant or malevolent question. This is a steady state of mean impedance during breathing, which you model and which you take the raw data for. So what if you have large interbreath changes during breathing, which totally rearrange the mechanical properties in almost all compartments involved, but probably in different ways?
Yeah, I'm assuming you're right.
I know this is very nasty, but
yeah. I have no good answer to that except to acknowledge that that is a distinct possibility, and I made the assumption that it was a stationary system during the measurement. Yes.
Okay,
I think one more question from Peter, and then Jason, you can do the introductions of Davido Bizzuto from Milan.
Okay.
Quick thing, Jason, terrific talk, really enjoyed it, and Jeff's comments. One of the things you assumed was that there was a consistent ratio, I think, in radiuses between the different units and the daughter units. I just wonder in disease states whether that's a fair assumption, given that you're not just dealing with the heterogeneity of branching of the airway trees, but you're also dealing with the way in which disease affects different units, and that could impact on different models. The nice thing about your asthma example, obese asthma, was that there wasn't anything intrapulmonary that might disturb things, but I just wonder whether or not that would hold true in other circumstances.
Well, that's a very good question. In fact, something I didn't say that I've done quite a lot of work on is I've extended this model in a slightly different form where I can allow, even though the average structure of the airway tree is deterministic, I can randomly vary with a certain coefficient of variation, all the radii, to allow for, stochastic variation in airway dimensions. And on top of that, if you do that, I can also play a game that I played in mice about 15 years ago. We're saying that there's a critical radius, that if any airway gets below that radius, it shuts completely. And so that you have a different mechanism now for elastance to go up, which is not that the intrinsic elastance is higher, but probably more realistically, that in those obese individuals and the asthmatics, you're actually getting diffuse small airway closure. And I can also put that into the model, and it describes the data pretty well as well, but I didn't want to get into those details here, but it's a good point.
Okay, Jason. So did you get a chance to get to know Davide Buzzotto from Milan, and can you do the introduction?
Sure, I can certainly do an introduction. So this is Davide Buzzotto from the Politecnico of Milan. I did meet Davide briefly at the ATS meeting in San Francisco, which was nice. So I feel qualified to give him an introduction, even though we basically just sit by and I listen to him talk about his work. But he's going to talk to us now about validation of a novel, small, handheld, turbine-based oscillometry device, and I'll hand over to him.
All right, so I'm sharing the screen. Do you see it?
Yes.
Not
Do you
yet.
hear me?
Yep, there it is. It's good now.
Okay,
Yeah.
thank you very much.
This is the non-presentation mode, however, which we have your full slide deck. But it's good enough if that's what you're going to do. Worked for Sylvia just fine. Ah, you've got it now.
Okay. Okay, so first of all, thank you very much for the opportunity of presenting this work today. I'm a bioengineer, so from Politecnico Milano University. Today, I will present to you our validation study on a novel, small, handheld, broad-based oscillometry device. So we know that the measurement of the mechanical input impedance of the respiratory system using oscillometry has gained a lot of interest in the last years. We can just look to the number of applications that are present on PubMed, and they are almost exponentially increasing. That is a very good thing. And especially it is really good that it is increasingly recognized as a clinical diagnostic tool. We also know that oscillometry is one of those techniques that do not require the collaboration of patients. So in principle, they can also be used for measuring the mechanical impedance of the respiratory system outside the primary function test lab and in an unsupervised way. One of the first pilot study that was made in 2002 was by the group of Ramon Farré, where they developed the first prototype of a portable force oscillation device for respiratory monitoring, and they also tested at patients' home. The results of the study showed that the unsupervised self-measurement of the respiratory resistance at patients' home provided a result that was really similar to those obtained by a technician in a lung function lab. So opening the world, we can say, to the application of oscillometry in a self-measurement, a supervised way. Further advancements in digital technologies allowed also to include oscillometry in smaller, less expensive, and also cloud-connected device. For example, for home monitoring and uploading the data using the internet to a data cloud that was then accessible by a clinician. But at the same time, these devices allowed also to perform studies on a day-by-day assessment, self-assessment of the area of obstruction that showed a very interesting thing. Here I reported just a couple of examples. For example, we can see that the increased day-by-day variability is a specific feature of asthma. Here I reported an example of one of these papers that showed that the coefficient of variability of the inspiratory resistance is much higher in the asthmatic group compared to healthy subjects. And this distinction can be observed by using oscillometry, while using a spirometer and measuring just the peak expiratory flow did not show any difference between the two groups. At the same time, the variability of inspiratory resistance can also be used to early detect asthma exacerbation. In this study, the authors used a day-by-day assessment of inspiratory resistance to use to build a predictor of the probability of having adverse asthma outcomes in the next day following the measurement. In a very similar way, also on the day-by-day oscillometry can be used for early detection of exacerbation in COPD population, allowing to have prompt intervention. We had the Crohn's study and Zimmerman in 2020. But also, other than that, this study showed that the adherence to the daily test with oscillometry is really high. This is a table extracted from the Crohn's study with data acquired from 312 patients monitored day by day for 9 months. And we can see that the adherence to the daily test by oscillometry was around 90%, so really high. Now, even if we have all these studies, we know that one of the problems related to the oscillometry now is the setup that might be still heavy, cumbersome, because it relies on some kind of actuators that can be a loudspeaker, but there are also different types of actuators that can be used that produces the oscillations that are superimposed to the breathing pattern of the patient. The patient has to breathe through a tube, and also, of course, this tube increases the dead space. We need in some way to reduce the dead space or remove in some way the carbon dioxide. So even if we can reduce a lot in the size and the weight of some of these components, there is a limit to the minimum size and also costs associated with the setup, associated to the architecture of this setup. A different approach that has been developed in the last years is based on a blower or a fan to produce the flow oscillations. We can see a diagram here on the right, while the patient can breathe through it. First of all, we can see that the dimension of this device can be really small compared to the classic FOT setup. At the same time, the overall dead space is very limited, and also the load superimposed by the device to the spontaneous breathing activity can be very limited. This is a prototype that has been developed, and now it is in validation stage, and it is developed by Restec SRL in Milano. And we are going to see here the rendering of the device. We can see the blower housing here on the left that hosts the blower, and at the same time hosts also the flow and pressure sensor and the connection for the mouthpiece for the patient. This part can be removed to be washed and cleaned between one measurement and the other. And at the same time, there is a touch screen that provides the results of the measurements and it can be used to select the start and stop of the measurement. It is also equipped with a pulse oximeter to have a measurement of SpO2 during the tests, and it is powered by a rechargeable battery, so it is usable in different conditions. The device can produce single frequency oscillations at 5 Hz, as well as pseudo-random noise with frequency content of 5, 11, 19 Hz. And it has also an integrated 4G module for uploading the results of the measurement to the data cloud. The weight is very limited as the dead space, and the breathing load is less than 1 centimeter of water as required for technical standards. So the aim of this presentation was to present to you the validation study that we did for validating this kind of device. So the device has been validated against a commercial one, already certified and commercially available, the Resmo ProFall V3, again by Restec, using an ad hoc active test lung. The test lung was made of one resistance. We used 2 different values, different combinations of bottles made of glass to reproduce different values of reactants. We also used a breathing pattern generator, flow volume generator, to simulate pre-recorded breathing patterns with a different respiratory rate, tidal volumes, and so on. And we also added the capability to simulate expiratory flow limitation by connecting an additional compliance during the inspiratory phase only, while excluding it during the expiratory one, to simulate the variation in reactance between the inspiratory and expiratory phases. We tested the handheld device at 5 Hz and with a pseudo-random noise. Here we can see the experimental setup. So we had the FOT device connected to the resistance and the compliance. The compliance was also connected to the breathing generator with using a high resistive path, and the inspiratory compliance was controlled with an electronic valve to connect it only during the inspiration and disconnecting during the expiration, of course, in synchronization with the breathing generator. Here I reported the results of an example of the results during the oscillations at 5 Hz. You can see that the traces of flow, pressure, resistance, and reactance as function of time. First of all, you can see the oscillations that the closed loop control on the amplitude maintain the amplitude almost at the same value during the different phase of the breathing pattern. And we can also see the difference in the measurement of reactance during the inspiratory and expiratory phase typical of EFL. Here I just summarize all the results that we obtained from the test by changing the compliances, the resistances, and so on. We can see on the left the measurement of the resistance, on the right the reactance, with the measurement done with the handheld device and the measurement done with our reference system. We can see that for all the measurement for both resistance and reactance, we have the two systems that have a very good agreement in the measurement of all the indices of the within breath indices, and all the measurements are within this dashed line that represents the ±5% error between the two systems. At the same time, we can say the same for the measurement of the delta XRS during the tests with expiratory flow limitation. You can see that for both for the system can identify correctly the delta XRS, and all the measurements are within the 20% error. In this slide is just another example that for the measurement done during the application of the pseudo-random noise. You can see again the flow, pressure, and the resistive and reactive components at the different frequencies. And we can see that the blower is able to generate also a pressure signal with a higher frequency content till 19 Hz. Here again, I've summarized all the results of the study with all the permutation of compliances and resistances. On the left, again, we have the resistance, on the right, the reactance. You can see that for all the frequencies, the resistance is almost the same for the handheld device compared to the reference one. The regression line is almost the identity line, so they are very good agreement in the measure of resistance. For we can say the same for the reactance. The regression line is almost the identity line. We have some points, some tests at a higher frequency that are outside the ±10% error, but I know that they're fixing this behavior that was probably due to a frequency response of the flow meter. And so in conclusion, we can say that the fan or blower-based oscillometry device can be used for providing accurate measurement of the respiratory impedance, also with in-breath analysis. And at the same time, the overall device is much smaller and lightweight, less expensive compared to the current approaches, or current approaches that can provide both resistance and reactance. And of course, these features can enable a lot of studies, a lot of new application of oscillometry, especially outside the lung function test, for example, for home monitoring, points of care, general practitioner, pharmacies, and so on. So really opening the future to a lot of new applications for oscillometry. So thank you very much for your attention, and of course, I'm available for questions.
Thank you very much, David. That's a very natty little device you guys have developed, and I think it's going to have a lot of application. And it certainly seems to be working well. In the interest of time, I won't ask too many questions, but I did want to ask about your cheek support device, because this being a portable device, you need to have one hand to hold the thing in front of you. So you can't obviously use both hands to support your cheeks. How effective is that? Have you done any studies where you compare that with and without those things compared to cheek support with both hands?
Well, not yet, because in this study was only for the in vitro measurements of different loads. So we didn't evaluate also the effect of the cheek holder that comes with the device. For that, we are waiting for the possibility to do some in vivo measurements that we are not allowed to do that at the moment. But it will be for sure one of the next phases. Yeah.
Well, I'll make a quick suggestion there, because we're working on a measurement of the interrupter technique for home monitoring, and holding a one-hand maneuver is not a bad surrogate. It's not perfect, but you could try playing with and without that. I think, Peter, you had a question.
Turn the sound back on and even the picture. I think this is a great device. It's really interesting, and it's going to be important. As regards the cheek support, I just wonder whether a stand to place the device on so that you can do the cheek support conventionally might be a way around this. It's a matter of how you make it. And therefore, you might then be able to standardize some of the potential differences about how the head is related to that. You do need to standardize a head position as you're doing this. My other real question, though, is can you get intra-breath variability? You implied you could get delta XRS out of this, so presumably you can get inspiratory and expiratory resistance and reactance measurements at least at 5 Hertz. And how do they look compared with the model data? You presented as, I think, the average over the breath. I just wonder whether the intra-breath variability was the same within the model.
Okay, yeah. So for answering the first question, the device, I didn't mention that, I forgot about that, but they also come with an accelerometer that is used to monitor the position of the head during the oscillometry. So it is standardized, and if the position is not correct, it will not do the measurement or provide some kind of error and saying the patient to move the head down or up.
Excellent.
So for what concerns the inspiratory resistance, reactance, and the difference between them, so the device is able to measure inspiratory and expiratory resistance and reactance in a very effective way. We have seen before the graphs with the multi-frequency signal that were very good, and also for the single frequency that they were very good for both inspiratory and expiratory. We didn't add a validation study for measuring the variability, since for validating the capability of the device to measure correct the variability, we need to change the in vitro model with rapid changes with every breath. So it is not easy to do that in vitro. But
thank you.
Yeah, but I'm sure that when we will be able to do.
Okay, so Jeff and Zoli, and then we'll move on to Sam's talk.
Thank you very much, David. It was a pleasure to meet you at ATS and hold the device. It's quite nifty. Just a quick question: is there a reason why it's you currently limited it to 19 hertz, that you do 5, 11, and 19. For those who might want to do AX for children or something, do you intend to actually go to higher frequencies, or is there a reason why it's stuck at 19?
Well, at the moment we are using up to 19 Hz because of a current limit that is imposed by the use of the battery power. That when you use a battery power device, in particular a medical device, and the amount of power that can be provided by the battery is limited. So we are limited by the current that can go to the blower. Said that, I'm not sure that with a blower it will be possible to go much higher in frequency, because of course you have to change the velocity of the blower with a very high acceleration. So I don't know if it will be possible to go too much higher. I know that we did some test laboratories and we arrived till even 25, 30 Hertz, but they were test laboratories. So,
well, thank you. Yeah, no, very good.
Yeah.
And Zoli, your mute is on. Your microphone is not on.
Thank you. Congratulations, David. It looks a very, very nice little thing. And hopefully it will work well, circumvent all the problems which have been raised in this discussion. I just have a comment, or not a comment, a question. Is this device robust enough to deliver the same amplitude and frequency components of the signal at extreme breathing circumstances, hyperventilation, for instance? This is a question. And the other one is the device able to operate at elevated airway opening pressures, like in non-invasive pressure support?
Right, okay, so for answering the first question, we did the validation study using the flow volume simulator to effectively use pre-recorded breathing patterns, and one of these was from also pediatric. We did also another one with a COPD subject, with the measurement obtained from a COPD subject. So it is able to maintain the correct amplitude also with a high variation of flow. So it works pretty well in this case. Oh, sorry, the second question was
the elevated airway opening pressure. So in a closed
yeah. So the device is now realized to impose the much lower pressure possible. We can say the CPAP it's very low. Of course, it uses a blower. So in principle, it can also be used for operating at a higher pressure. Now, for monitoring, we would like to maintain the mean pressure as low as possible, in order to not change the expiratory length volume.
Okay.
Okay, David, thank you very, very much. I look forward to meeting you in person in the future, and congratulations on your device. And I saw Raffaele in the audience, so tip of the hat, Raffaele. I like what I see. We'll hand the podium over to Sam Bayat from Grenoble, who's going to talk to us about tidal changes of respiratory resistance associated with a history of asthma diagnosis in children. And Shannon Simpson will be coming from the Evening of Australia to moderate the talk. So this podium is yours, Sam. Thanks.
Thanks very much, Ron, for the introduction. I don't know if you can see my screen, my slide.
Yeah, it looks great. Yeah. You can see it well.
Okay, great. Thanks very much. So, okay, this is sort of an application study. As you know, the prevalence of respiratory symptoms in infants is high. And for example, approximately 30% of children in the general population will present at least one episode of wheezing before the age of 3 years. And of these wheezers, about a third will go on to develop persistent asthma. Epidemiological studies have shown that early lung development is an important determinant of later lung function. and as you know, a major advantage of oscillometry is that because it requires no active participation, it can be, it's easy to use in young kids and even in infants. And that's a study by Diane Gray that showed in South African infants that showed that actually it's feasible to do this in non-sedated infants. So another point is that recent studies have shown that intra-breath variations in resistance and reactance are sensitive in detecting airway obstruction and also mechanical heterogeneity. And this is both in children and in adults. Also intra-breath parameters were even shown to predict the risk of future lower respiratory tract illness. And also this was in a South African study, a cohort. So here the question is whether we can use the intra-breath oscillometry and to see if a history of lower respiratory tract illness, wheezing, or asthma in the first years of life actually affect these intra-breath oscillometry parameters later on at the age of 3 years. So the goal of this study was to assess the relation between the intra-breath oscillometry parameters and a history of illness, assuming that these parameters would be sensitive. The intra-breath oscillometry parameters would be sensitive to detect a history of lower respiratory tract illness. So the recruited children were part of the CEPAGE couple-child cohort, and briefly this cohort aims at assessing the effect of outdoor and indoor air pollution and environmental exposures such as particles, nitrous oxide, volatile organic compounds, etc. And all of these are actively sampled using a device that's carried for 1 week by the mothers during the pregnancy, and outcomes such as respiratory health, growth, or neurodevelopment are assessed later on in the children. And this is a single center cohort, and all the mothers and infants were recruited in the Grenoble area. Of course, appropriate ERB approval was obtained, and so the respiratory health was assessed repeatedly using a modified ISAC questionnaire and on respiratory symptoms, and initially at 2 months and then each year, and particularly the history of physician-diagnosed asthma, wheezing, bronchitis, and bronchiolitis were assessed. And also at 2 months, FRC and LCI were measured using multiple breath washout. And then at 3 years, respiratory impedance was measured using the TremorFlow device, and both spectral measurements and 10 Hertz intra-breath measurements were measured. And also atopy was assessed using skin prick tests. So this slide shows the study diagram, and as you can see, I'll move on to the study diagram that shows the 471 couple-child trios were included in the initially recruited. Of these, 384 attended the 3-year visit, and then 272 performed oscillometry, and 251 children were able to perform both spectral measurements, reproducible and acceptable spectral measurements, as well as at least one intra-breath measurement. So the following slide shows the population characteristics. The average age was 37.4 months, and the children measured on average almost 96 centimeters and weighed about 15 kilos. 22% were exposed to tobacco smoke, passive tobacco smoke. The level of parental education was high in this population. About 74% of the parents were college graduates. 88% were breastfed at 2 months. And the 8% of the children were born before 37 weeks gestation age. And about 30%, 27.8%, had a parental history of asthma. So 12% of the children had doctor-diagnosed asthma ever, about 33.6% wheezing ever, 37.8 bronchiolitis, and 21% bronchitis. So the burden of lower respiratory tract illness was rather high. Mean LCI was 7.6. FRC on average was 105 ml. And about almost 12% had a positive skin prick test. So here's what the interbreath, a sample interbreath measurement looks like. Now in this particular child, as you can see, the arrow shows the inspiratory limb, and during inspiration, the resistance decreases, and during expiration, it goes to a higher value becomes maximal during expiration, and then goes back down at the end of expiration. So I won't get into details of why this happens, but you can see that the resistance outcomes, the interbreath resistance outcomes, were measured at the end of expiration and of inspiration when at zero flow. And same with reactance. Now note that normally in normal cases, the reactance slightly decreases during inspiration, supposedly due to the contribution of chest wall elastance. But here in this case, and also in obstructive cases, it slightly increases, and during inspiration, possibly due to better homogeneity with inspiration. So it's just an example. Now, the univariable analysis showed that associations between spectral oscillometry parameters and the subject characteristics. And as you can see, the only R719, that are frequency dependence of resistance depended on sex. R7, X7, and AX all depended on height, but not weight. X7 and AX were associated with passive tobacco smoke exposure, as you can see here. And R7 and AX were also associated with a positive skin prick test. Now, regarding the interbreath oscillometry parameters, these were associated with both height and weight. The delta R, the resistance change during the respiratory cycle, depended as well on age. And these parameters also depend on the level of parental education. The interbreath reactance depended essentially on height, and also inspiratory resistance and reactance both depended on breastfeeding. Now, when we look at the multivariable analysis, and this initial model was adjusted on age, sex, and height, here R7 was associated with physician-diagnosed asthma and bronchitis, while AX was associated with ever bronchitis or bronchiolitis. It's down here. All of the interbreath resistance parameters, which is the N inspiratory resistance, the N expiratory resistance, and the delta R, the resistance change, these were all associated with asthma, ever diagnosis of asthma. Delta R was further associated with ever wheezing. Now, when these models were further adjusted on the other confounders, which are tobacco smoke exposure, passive smoke exposure, breastfeeding, parental history of asthma, or child allergic sensitization, none of these really fundamentally changed the associations between either the spectral or the interbreath parameters and the history of lower respiratory tract illness. The also further adjustment on LCI didn't change fundamentally these associations, and neither did the adjustment on FRC. So in conclusion, our data suggests that, first of all, they suggest a causal link between the history of early life lower respiratory tract illness and respiratory symptoms, and decreased lung function in a population-based 3-year-old population with 3-year-old children, and this is independent of lung function at 2 months. And also, both spectral and interbreath oscillometry indices were significantly associated with the history of LRTI. And also, I think these data suggest encourage the use of intrabreath oscillometry as a sensitive outcome measure in epidemiologic cohorts, particularly in population-based cohorts. And also the future perspective of this kind of work is to assess in the same cohort is to assess the effect of various environmental pollutants and exposures on later lung function. Now, currently the kids in this cohort are turning 5, and soon, hopefully the next set of measurements will begin. And with that, I'd like to end this talk, and I'd be happy to answer any questions. Thank you.
Well, Sam, thank you very much. Shannon, are you still with us to take over the moderating?
Certainly am. Thank you so much, Sam. That was a really interesting talk. I've got a couple of questions just to kick off while people are thinking about the questions. I'm just wondering, in terms of your overlap of your populations, we know that, for example, if you get bronchiolitis in the first year of life, you're more likely to end up in that asthma group or later wheezing group. Can you just talk to us a little bit about how you positioned each of those clinical phenotypes? Is there overlap at all?
Well, certainly overlap is possible, and the difficulty with epidemiological studies and also the questionnaire-based data is that oftentimes you may lack that kind of resolution in terms of here you have a resolution of 1 year, and the question is, did your child over the past year, past 12 months, have bronchiolitis or have bronchitis or have a physician-diagnosed asthma? There's, in terms of determining when that happened. And one thing that we do know is that none of the children at the time of the measurement were ill. So these are not like intermittently asthmatic children. We know that they historically had a diagnosis of asthma. But that's a very good question. I think, did these happen at the same time? Did bronchitis precede the wheezing? How did these interact with the diagnosis of asthma? And all that is not extremely clear in questionnaire-based data.
Yeah, I think that would be something that'd be really interesting to look at. One of the other things I found really interesting about your data was that parental education level appeared to be almost the strongest predictor of the intrabreath outcomes. And I'm just wondering if you've got a sense of what might be driving that. Are we talking about differences in nutrition or air pollution or more early life infection from crowded living space? Have you got any kind of clues as to what might be driving that?
That's a very good question. It could be all of the above, because my guess is that this is related to socioeconomic status, and because the direction of the association is that those kids with higher parental education tended to have lower resistance and higher reactance, in a sense, less compromised respiratory mechanics. So I mean, it sounds like all of those factors could contribute, and those that are related to socioeconomic conditions. Yeah, that's a good question. Also, breastfeeding was another factor, and that's a surprising one, because the children were breastfed, still breastfed at 2 months, tended to have higher resistance and lower reactance, unexpectedly. But I don't have an explanation for that.
I see Larry's got a question, so I'm going to throw over to him.
Right, thank you, Sam. That was a beautiful presentation, very interesting data. I was kind of surprised that the results were independent of LCI at 2 months, in that, there's been a lot of talk that sort of the die is cast, and you start off at a lower lung function early on, you track that, although other data suggests that there's a certain segment who will catch up and sort of normalize. Why is it the insensitivity of LCI, or why do you think that the results seemed independent of that? What happens if you dichotomized into those who were below the lower limit or above the lower limit norm, or
That's a very good question. Also, when we started out in this study, definitely there's a lot of literature about association of lower lung function at birth and later illness and lower lung function later in life. So definitely there's an association there. Now, the question is whether when you get a lower respiratory tract illness, often due to viral infection, is there also an independent effect of that infection on lung function later on? And I think the associations go both ways. That's my take on this at this stage, is that a lower lung function at birth definitely compromises your later lung function in life, and also raises the risk of lower respiratory tract illness. But there is also the other association, the opposite association also is there, where if you get pneumonia or bronchitis or illness or asthma for that matter, that at least our data show that at 3 years, in the first years of life, then at 3 years your lung function is likely lower, and that is independent of your susceptibility due to lower lung function at birth. So there is an independent effect.
Thanks, Sam. Sylvia, would you like to come on and ask Sam your question?
Yes, I was just wondering on this topic whether it would be useful to look at phase 3 slopes in this case, because if I get the name right, I think Sonapa showed a correlation between wheezing and ESCON. Well, for those who that means something too. So it was basically the phase 3 slope. So maybe it's worthwhile to have a look at these same data from which you extracted the LCI and just look at the phase 3 slopes.
Definitely. Definitely, Sylvia. I mean, if you're interested, that definitely I can dig out the data and we could work on it.
Okay.
Great. Fantastic. Well, even setting collaborations. Before I hand back, I'd just like to say, Sam, that's a wonderful feat measuring 253-year-olds. I've measured some 3-year-olds and 250 of them is very impressive. So well done on putting that together to present to everybody today.
Thank you, Shannon. Yeah, thanks.
Well, Sam, Shannon, thank you very, very much. And just remind everybody that this is the one conference where the discussion is more important than the clock. And so even though we're approaching the last 5 minutes of 2 hours, Jeff, we've got the full 20 minutes for you. The only fly in the ointment might be if your expected washing machine happens to be delivered during your talk, but we'll forgive you for that. So it's with great pleasure that longstanding friend and colleague Jeff Maxim from Dalhousie is going to be talking to us about some important issues in quality control and at the same time saving time with oscillometry studies. And Zoltan Antosh, who obviously needs zero introduction in this audience, will be moderating. So thanks, Jeff, and we look forward to your talk.
All right, is the screen up for everyone?
Yep, it's on full screen.
Great. Right, so yeah, I hope I can save time with this talk. It's in the title. So this is going to be a quality control talk, and I have to thank at the outset my student Anas Abufarda, who's deferred the presentation to me. I am a co-founder of Thoracis, so I have a disclosure there, and I'm a sometimes advisor, but I don't get money, except for some small amount of shares. All right. The current standards for oscillometry for quality control, there's a few of them, but the main one is that the coefficient of variation of the resistance at 5 Hertz should be less than 0.1. So that's 10% in adults or less than 15% in children. And that was published just in 2020. However, we measure from 5 to 40 Hertz, and we use those measurements over resistance and reactance to do things like measure the frequency dependence of resistance, and we also measure it from the reactance, the area. But our quality control is just on one point of that curve. So should we include the additional information, will that help us to do any better? And how does optimizing for low coefficient of variation affect feasibility and accuracy? Actually, what does it do in general could be a very good question. Because when you want to get it lower, you might be changing the answers you get. All right, so we have some access to data sets from which we began this study. And one is the child study here in Canada. And we use the 5-year age group, and we have 550 kids. And we have oscillometry from all of them. And these data sets, and we have a data set from Ron Danderand, which includes largely COPD diagnosed subjects and a few others. And we have a group of children, again, aged 3 years old, all diagnosed with weeds. And these data sets are good because they have multiple measurements in them, from 6 to 12 in child, and 3 or 5 in the COPD, and 3 to 8 in wheezy ER. So currently in practice, and it varies from device to device, but if the CV is greater than the threshold, so you're faced with a failed test. My current measurement has a CV of 20%, so it's a child, so that's higher than 15. But if I do another measurement or have multiple measurements, I can choose amongst those to get 3 that actually meet the criteria, and away I go. But a more efficient approach would be to collect data and stop when any of the 3 repeated measures meet the criteria. So instead of making sure I've got a CV less than the 0.1 or 0.15, having the device actually figure it out for me and stopping. So we've already been through what a typical impedance test looks like. This is off of a TremoFlow. You get repeated measures. The different thin lines show some variability around the mean, and the thick line is the mean. So what did we do? We attempted many combinations of optimizing to lower the coefficient of variation on the y-axis versus frequency using resistances, using reactances, and also the combination, the impedance, or using the absolute value, which includes resistance and reactance at different frequencies instead of just R5, to reduce the variation of the ensemble of measurements that we have in front of us. And I won't go through all of the different results, because it turned out that the best one was an inverse frequency weighted sum of absolute value of impedance. So basically this formula here. So if you get the coefficient of variation of the result of this sum less than 10%, that's what we tried to do and the results are on this graph. So if you don't do any quality control, you just accept the measurements that come in. So the measurements that come in from child had a coefficient of variation ranging from 0.13 down to 0.11. And these are the means with the standard error bars. So that means a large number of patients were actually rejected if you kept all the measurements. Now, of course, you manually go in and select one so that they are more acceptable. Or if you automatically choose R5, you'll get a coefficient of variations at the different frequencies according to this. And the means approach 0.1. Since this is standard error, there's still a few that are rejected if you paid attention to 20 hertz. You get a slightly better coefficient of variation if you optimize according to Z1 over F. And the improvements don't look very big, but the improvements in performance and feasibility and efficiency are where it matters, as I'll show. But we did find that doing this improved the coefficient of variation at all frequencies versus not doing anything, and also versus just the one that's in the technical standard, R5, significant. It also improved the coefficient in both the resistance and the reactance. And I'm not showing it, but it also minimized the coefficients if you go and measure what the coefficient of variations are in R5 minus 19, for example, or AX. What happens if you look at feasibility? Well, if you have an automatic criteria that selects out easily for you whether or not you pass an acceptance criteria, and in this case, we've modified it slightly so that it is 10% based on absolute value of weighted impedance, you get, instead of 60% if you do nothing, so in these children, 40% of the data is unusable unless you manually go in and start to pick out unacceptable recordings. But after this automated procedure, you get 100% acceptability. So that improves the test. And it also reduces the number of measurements you need to meet the CV criteria, which was 6 before QA. After QA, you only need 3, of course. but the 3 that you use may not be the first 3. And so if you measure and stop, on average, that was about 4.1 with a standard deviation of 0.5. And we got similar results for the 3-year-olds. Except interestingly, on that piece of data, we had an expert go through and manually select data in a way that was not looking at the resistance per se, but looking at the pressure and flow for odd breathing patterns. So large breaths, gaps in the breathing, and rejecting that kind of data. And that actually didn't improve the feasibility at all. It was worse than not doing anything. But the automated quality assurance technique that I've described at least improved it to 76%. And it's understandable that these are 3-year-olds, so their data is more variable. So it's worse than the 5-year-olds. And a similar improvement in efficiency. What those results mean is that improved feasibility would mean fewer subjects are needed if you're doing this as a part of a research study, say a drug trial. You would need lower N to get the same power. Improved efficiency means you can do the measurement in a shorter amount of time. But I haven't talked about accuracy because it's something that even those of us who wrote the standard, we assume that optimizing for improved coefficient of variation is getting better data. It looks more reproducible because we filtered out ones that are outliers that don't seem to fit. But is it really truly more accurate? So you can't do that with real data. You have to use a model. And so we first wanted to do a realistic model. So we looked at the variability we had within subjects. And this is a slide of just, I guess it's 9 subjects. And these are subjects chosen that all had coefficient of variation greater than 15% from their impedance. They also had coefficient of variation greater than 15% from their R5. And these are the multiple measures. And there's a little number there, you don't have to see it, but there's 5 measurements here, and there was, looks like 8 measurements from this patient. And what's highlighted here, this ANAS has highlighted one way to look at outliers, and this is our most severe choice of outliers, so close to the mean. It's 1.5 standard deviations. You can identify outliers and just see what's happening if there are any of that sort of kind of artifact happening in your data, changing this variable. So what you see is that we observed that the algorithm tended to prefer clustered central values. So these triangles are the values the algorithm chose and rejected the other ones to meet the criteria of coefficient of variation less than 15%. So originally, using all the values, this is unacceptable. But after the algorithm, these triangles are the ones the algorithm chooses. But sometimes it doesn't. Not as often as it chooses the center, but sometimes it chooses these ones. And so would a human overreader actually say that this is the correct impedance, or it should be something in the middle? Those are difficult questions to answer, but I'm making you aware that one size fits all algorithm does have limitations probably. But what we also did with this data, apart from learning of how the algorithm is working, is that we used it to identify what's happening to our normal variability, let's say, and identifying outliers very not in a rigorous way, or perhaps in a rigorous way, but not in a very fair way, because we don't actually know if those outliers are not physiologically possible and are actually due to artifacts such as holding the breath or talking or coming off, leaks and that sort of thing. But when we do identify outliers with that criteria of 1.5 standard deviation around the mean, this shows the distribution of resistances, just R5 in this case, around the population of children of age 5. And with outliers, it's in blue, it's a probability density function. And with outliers, it's in red. And you can see that, yes, we've eliminated some of these high measurements here and some of the bottom measurements here. The ones that have been removed have this distribution if we normalize them each to their mean, each to their mean, which produces a 1 for the middle. So you can imagine that what's happening here is there's some variation that's inherent in the patient, and occasionally they go out of range. It's a very rough guess at what might be happening. But using that as our model for creating known values of resistance with randomly chosen noise from this distribution, we can actually test the performance of this algorithm with knowing the true value and actually calculate the accuracy. So in this particular example that I'm going to show you, we just chose every patient to have the same mean, and we used to calculate a resistance for all frequencies. We would do a curve fit to the mean resistance across all the subjects, and the same thing for reactances. What we want to do in future is choose from that physiological distribution, but I don't actually think it would make much difference. It's actually the variation and how often and what you do with the outliers that matters. When we add outliers to that distribution and then apply the algorithm to choose to optimize for feasibility, which means reducing the coefficient of variation according to this criteria, absolute value of Z, to try to get it below 15%. What ANAS did was model the impedance in 1,000 subjects. It's a model, you can just have the computer do many, many subjects so you know the truth. And each subject had 5 measurements, each contaminated with outliers. And we would have different numbers of subjects that had outliers. It turned out when we looked at the data, depends on the level of standard deviation that you decide for an outlier, but with a 1.5, which is a very strict definition, 70% of the patients had at least one outlier. And actually it was kind of rare to have more than one. So that was the most common thing. But the results show that with no outliers, the algorithm actually seems to make it a little worse, but I wouldn't call this a meaningful difference. But the algorithm does improve the accuracy when comparing the mean squared error of this cost function, that you can produce the same type of curves for R5 or R5 minus 19 or AX or any of our outcome measures and show that it's improved. Now we chose a group of subjects with high variation in order to trigger the algorithm. What we really need to do is actually do the distribution that actually exists. So a few patients with 5% coefficient of variation, some with 10, some with 15, some with 20, and see how it performs. But at least at this level, it seems to be improving the accuracy. And interestingly, not affected by the, when we're calculating it in a group, not affected by the number of subjects that actually have these problematic outliers. Finally, I'll have a couple more slides where we also did a similar approach to reducing the variability in within-breath tracking of ZRS. So within-breath tracking divides measures of pressure and flow into individual breaths, and then calculates resistance and reactance from each of these during the breaths, and usually plots them resistance versus flow or resistance versus frequency like this. And so these are patients actually with chronic lung allograft disease, or in a study of patients at risk with chronic lung allograft disease, so lung transplant patients. And you can see that it's quite noisy. Each breath follows a very odd looking trajectory, right? And so you get, if you try to do the average resistance or average reactance, including all your patients, you'd have high coefficient of variability versus for those measurements, if you just did the average or the sum or whatever you wanted to do to quantify the variation. So we did this very similar thing, is we identified the resistance versus time versus each breath and the reactance versus time in each breath, and chose 3 breaths that had the lowest difference between all 3. And those are the thick curves that you see there. So when you do that, what are the results? Well, I'm also, just before I show you the results, we also produced a model where we chose typical values of resistance, elastance, and inertances, and we added variation. So elastance with mean variation plus a variable amount of variation divided, normalized to the mean. Same with the resistance. And we would also add breathing noise to make it realistic, which was very similar to the noise measured in real life. So what happens when you do the algorithm, trying to choose 3 good breaths? And with increasing levels of noise, so this is mean squared error on the y-axis and increasing noise. At the beginning, the algorithm isn't important. But then with increasing levels of noise in the breathing, pressure and flow, you get an improvement, and it seems to be a scaled improvement in accuracy of your resistance versus time and your reactance versus time. This is resistance root mean squared error, and the 10% error initially, say picking this point here, is reduced to 5% with an alpha of 1 here. And this is the reactance. The reactance has larger error to begin with, and it's reduced to 25%. So you're getting more accurate applying an algorithm such as this. This may not be the only algorithm that works or helps, and we haven't really worked a lot to optimize it. It's just showing one of the possibilities that might be useful to those out there. So not a kind of a different kind of talk, talking about what we're doing when we're actually trying to meet that criteria of resistance of 5 hertz less than 15% in children or 10% in adults, and showing that you can do a little bit better if you use ZRS as a frequency weighted thing, which resulted in improved repeatability. The coefficient of variation was lower, improved efficiency. So you didn't need to measure the same number of patients or measurements in this patients. And you also had improved feasibility, which means more patients actually passed the test. And finally, there seemed to be an improvement of accuracy, but we have yet to actually measure at different levels of variation, coefficient of variation. An improvement in the time tracking. So I think we learned a little bit about what happens in real life when you look at the variation within subjects and across subjects, and are learning a bit more about what we're doing when we're applying these quality control metrics, and they can be improved. Thank you very much. And I'd very much like to thank Anas, who is the student who did all of the work here, Anas Abufarda, and help from other students in the lab and my collaborators, Ron Vander, PJ, and Sick Kids, and some of her team. Thank you very much.
Well, Jeff, thank you very, very much. And Zoli, I'll let you step in and lead off the discussion, moderating Jeff's talk.
Thank you very much. Thank you everyone for my plural assignment as discussants, but I would use only one singular role this time. Congratulations, Jeff. I enjoyed it very much. All the more, I was occupied by similar thoughts in these few weeks' time. So the first question, which must be very touching, that why the hell is resistance at the lowest frequency like R5 in this device and some other devices have this privilege to characterize a variability of respiratory impedance, whereas reactance is, I think it's not the underdog, it is an equal part of the impedance, all the more in several diseases. It is probably more important, like symptoms such as expiratory flow limitation, where the major information is coming from reactants. So why are we looking at resistance only at R5? Second question, which I have to ask myself as well, because in the 2003 recommendations, we simply declared the 15% variability for the lowest resistance. Nobody has explained why 15 and why is it 10 now? And it is not even empirical. It is just a declaration. So thank you very much again. Two questions. In your complex impedance approach to the variability, you have an inverse contribution by the highest frequencies, and accordingly, you have a bump, a local maximum at 20 hertz in the coefficients of variation of Z, which is probably a consequence of this modeling of the Z contributions, and might be important if you look at measures, quite popular measures like R5 minus R19 or R20 or something like that. So these are probably punished by this normalization. I'm not going to be very provocative, but it is really very important that if we are looking for the minimum variability of impedance within a session, a measurement session, we might probably lose some measure of intrinsic intrasession variability. Especially, I think, in children, this would be important. So to uniformize everything and coming out something which is leaving out the suspicious extreme values without any artifacts involved, of course, that would be probably a reduction of information which we can get from. The last comment from me, sorry for this disorganized string of thoughts, because I did not get your slides at the time it was promised. So let's stop here. And
okay, you're stopping there. All right, I thought there was one more. Okay, there was just that dig. Okay, good. Thank you very much. I assume the first questions are partly rhetorical. I mean, well, I wonder if they were actually. But what can I speak about? Why did we pick R5 as the sole measure to base our coefficient of variation on? We moved as a field away from coherence to variability. And we seem to have been very unfair at not addressing the reactance as a partner in our valued measurements that we have. And we also devalued other frequencies. And that's what we're trying to address. To be honest, I'm not sure why that was done. People have the most, it's not based on evidence. It would be based on expert opinion, which is the least valuable of the evidence that you can use if you're trying to make a technical standard. From experience, though, in dealing with these measurements, R5 is the best choice if you're going to pick any single frequency, because it has if you choose R11 or R20, R5's reliability is shot. You need to have R5 in your weighted measures to get any reasonable accuracy in R5 out of it. So R5 shared with R20 might be a good choice. We tried that, but we actually found a weighted measure to be even more important, which felt that weighting the lower frequencies, and I shouldn't be saying R5 because we're weighting all of the lower frequencies, like resistance being a high value at low frequencies, reactance is a high value away from zero at low frequencies. So it's important to include, I think for that reason, the low frequencies predominantly rather than the higher frequencies. So that addresses that point. Now it's a challenge to remember your second last point, which I did have a thought on. Can you remind me?
Why just Z? Or sorry, why is just R5? Why not reactance included? That you have solved this problem.
Yeah. So I think I answered that question. So I think we'll probably
the next question was the bump in the CV.
That's right, the bump
issue.
That's a good point. It's probable due to the fact that reactance is turning from negative to positive at near those frequencies, and at that frequency, the impedance is almost all resistive. I don't actually fully understand how that translates into a bump in the variability. We've seen the bump even if you just optimize R5. I don't think you see as much of a bump if you optimize R20, but then R5 goes nuts. So
yes, probably it's an artifact and just reflecting that impedance in general has a minimum at about 20 hertz or something.
I do remember the last point, which is a very important point, and which is if you start, because the criteria, they don't say directly to do this. The criteria as measurements are acceptable if you have at least 3 that are less than the CV of 0.15. If you have 3 measurements and they meet the criteria, you're doing the best you can do according to the criteria. If you have 5 measurements and it doesn't meet the criteria and you throw out 2, that's something the technical standards are silent upon. And I think you're right. It's not always a good idea to throw out those other 2 to meet the criteria. I think you'd need a better reason to throw out the 2. In other words, it's an outlier. It obviously has a leak. It obviously, something like that. Then you can throw it out. It's a tough one to make a decision on in the way that we did.
Thank you, Jeff. I think Cindy.
Thanks, Ollie, and thanks, Jeff, for that. And I think we knew when we wrote the standards that it became obsolete almost as soon as we wrote them and published them. And I think just quickly to Zoli's point, I wonder if another reason for X not making it into the common practice, which is effectively what this was based on, as you say, rather than evidence, is that it tends to be more variable than R. And so it's difficult to pinpoint a fixed cutoff on the basis of variability for X. But I just wanted to make the point. I completely agree with you, Jeff, about the wanting to discourage people from continually making repeated measurements in order to achieve a somewhat arbitrary cutoff. And we approached this slightly differently from a different point of view last year when we looked at how this change in disease. And so in a paper by Louise Harkness last year, which you may have come across in the ERJ Open, we showed that when you compare normals with asthma and COPD, and admittedly in a very small number of subjects, you need an increasing number of measurements in order to achieve the cutoff when you have disease. And so effectively, you might even be removing signal the variability, an increased variability itself might be a signal in disease. And so whilst I appreciate your point about, trying to reduce variability in order to achieve better feasibility and better ability to discriminate between disease, we were starting to move away from the idea of trying to reduce variability and instead focusing on instead focusing on artifacts. So a quality control approach that's focused on making sure that the measurements that you have are artifact free rather than trying to reduce variability to that arbitrary cutoff. So I wondered what you thought of that. And then the follow-on question was that it also made me wonder, the algorithm that you presented in the second part of your talk, how does it perform? Does it perform differently between health and disease? Do you find that it has to work a little bit harder to try and reduce variability in disease? And does that say something? What does that say?
Do you mean the within breath when we tackle that? Yeah, no, we've only done a limited amount of work in that space. And it was on patients that were handy at the time. So we need more within breath data from disease and health to actually do that. So my within breath data that I have in my lab is a small group of subjects, and I couldn't really answer that question, I don't think, with that group. In terms of focusing on artifacts, almost all the manufacturers have some sort of artifact detection, but they tend to remove breaths or they remove values within the recording and improve that particular measurement. After you have your 3 measurements, there's nobody who's actually, no manufacturer at least, who's paying attention to artifacts. and doing anything with them. And so we're left with the criteria. And if we do the criteria, it has issues, which I think, which you raised and we all raised. And I hope I can include that in some kind of publication.
And, I think it was last year as well. We published a kind of a letter or advocating for a particular process for doing measurements in the laboratory, where you do pay attention to the CV, or the COV, but you start off by looking at artifacts first, and then looking at what the variability is after that, after you've ensured that artifacts are gone.
I agree with that. Yeah.
Thanks, Jeff.
Thank you. Great question.
Jolie, I think Peter had a question before Cindy. Peter, you there? And do you still have your question?
Oops. Sorry about that. I had a man from the bank worrying about a payment, so I disappeared quickly. Great talk, Jeff. Very thought-provoking. This stuff is fundamentally extremely dull. It's amazingly dull, and therefore it's incredibly important. Because one of the things that we need to sort out, and the discussion we've just had illustrates this, is the importance of what is physiologically important, as in the variation that Cindy was talking about, which then becomes a characteristic, rather like the first category of observations that in Jason's talk, and what is unhelpful. I thought what I wondered was, how long did it take the system? In other words, how would it influence the test duration if you were to adopt the system that you were adopting? Would you need to have people breathing for much longer than the standards that we now use? And I secondarily wondered is, would you be able to test this approach in a data set that has shown the kind of important physiological variations where variation is a key factor? It might be that you could improve the discrimination of those things, not weaken them. And to that extent, I think actually Cindy's group's nice data about exacerbation prediction in COPD would be good. So I think it would be very good if we could clean the data further and have a more generally logical way of setting standards rather than the rather illogical one we have now. But I think we don't want to throw the baby out with the bathwater. So I think that's a suggestion for further work. But practically, what's the implication for test duration?
So far, every indication is, it depends on how you practice. I've been advised by some labs, they see the technical standard and they basically say, we need to do 3 measurements. So we do 3 measurements. And if it's not acceptable, it's not acceptable. That patient doesn't make it into the study, right? And that seems rather harsh.
No, it's not been our approach.
Yeah, mostly people try to measure more, and they do an adaptive approach where they notice the CV is high. So they do a few more, like 8 or something like that, and hope there's some meaningful ones in there. And that's the caution that Cindy raised, that when you do that, and you raised it yourself, when you take away measurements because you're just trying to optimize for a CV, you might be biasing your result. So far, when we have large variability, it seems not to be the case. It improves the accuracy when we follow our algorithm. And the byproduct of following the algorithm is you're told when you have, as soon as you have 3 that are acceptable, you can stop measuring. So it's a shorter type of scenario than not knowing whether or not you've got enough that you meet the criteria. So you're always doing 8, for example. In this case, you sometimes do 3, sometimes do 5, sometimes do 6, but it has its limitations, as Cindy and you yourself raised.
Yeah.
And maybe an artifact approach
do
gets
some
away
more
from
work empirically to find out how important those are.
Yeah, I think so. And in terms of measuring variability itself, applying the algorithm to the 10 hertz data actually keeps, might be losing some of the variability that's occurring across multiple breaths because you're trying to focus in on the mean value in that subject. So I think if you want to know the standard deviation in the subject, that's a different question than when you want to know the mean. And applying the algorithm may be good for the mean, but certainly it's bad for the standard deviation.
Yeah, excellent. Thank you.
Zoli, do you have anything to add back to the comments before I close down the meeting?
No, I think we have enjoyed this talk. I didn't suppose at all.
Very dull topic.
Yes, yes. I think that the common statement which can be made at this point is the cautiousness about reducing the variability by any means, apart from obvious artifacts, to find the good balance between the two. Thank you very much.
Thank you.
Okay, well, thank you everybody who spoke, everybody who moderated, and to all of you who attended. The link will be the same next week as this week, but I will nonetheless send it out on the Monday before the meeting. So everybody stay safe, stay healthy, have a great week, and thank you once again. Bye-bye.
Thanks, Ron. Thanks, everyone.
Bye.
Thank you, Ron.
Bye-bye.
Thanks, everyone.
Thank you very much,
Thanks,
Ron.
Ron.